Welcome everybody, this is tutorial 3 and now in this one we're going to be tackling task 2 which is about implementing a heatx block in Aspen. So the question says that using the previously calculated heat duty, so the 180 kilowatts that we calculated before, we need to proceed with a shortcut design of a counter-current shell and tube heat exchanger. So besides, the question asks us to calculate or to determine how much ethylene glycol or EG we need for this heating service to reach an outlet temperature of this heating fluid of 42 degrees and a minimum approach of 15 degrees. And also, what is the temperature curve of this system? So as you know before, the minimum approach of 15, if we are targeting a temperature of 42 degrees, is already reached in both sides. So the minimum approach is the difference between the hot and cold fluid in each of the sides. So in this one, it will be 42 minus 23 degrees, and in the other one will be 27 minus 97. In both of them, we reach more than 15 degrees. So that's a design spec that we already have fulfilled. And now we need to know how to implement the heatx. So just to remind you, a heatx is a more rigorous heat exchanger, which means that we need two process streams instead of one as in the heater block. The first one is going to be the hot stream and the other one is going to be the cold stream. The good thing about this heatx block is that it's suitable for designing conventional shell and tube heat exchangers in a co-current counter-current mode. And it also allows us not only to calculate energy balances, but also to calculate pressure drops inside the equipment, exchanger areas, velocities, fouling, and so on. We can also have a default global U coefficient, and we can also manually select that one if we have found one in literature that is more representative for the service that we want to um, tackle in the process. So it's very versatile and it's really robust for shell and tube heat exchangers. And that's what we're going to do in this tutorial. So now we open Aspen, and as you can see, this was the previous task. Now we're going to start with a new simulation. And in this one, we're just waiting for the program to start. Yes. Here we can have a component ID again, R12 for the Freon. But now we're having also ethylene glycol, so EG, and you can find it in Aspen directly. The method is going to be the same as the previous one, so it's going to be an RTL. And because in the previous task we only had Freon, the binary interaction was not of interest. But now in this one, because we have also ethylene glycol, we need to have for the method we selected the binary parameters. So if you don't see them displayed here, you can go to the data banks, try to get all of these data banks and see if we can have some default parameters. We can see the activity in the control panel. It says that all pairs are 0, which means that these data banks were not able to give us some parameters. So the only chance we have now is just to estimate them using Unifac. So we're going to select it, we're going to run it again. And in principle, we have no errors, which means that Unifac did its job. And now we have seen that we get some nice parameters for the Freon ethylene glycol system. So now we're going to start with the simulation now that everything is prepared. And in this one, we're going to input the cold stream. In this one, it's going to be R12 in as before. And the specification was minus 23 degrees. The pressure was 8 bar atmospheric. And the flow was 12,000 kilograms per hour. Now the mole frac is going to be only one for Freon. And now we're going to have the other stream, which is going to be the hot stream, and is ethylene glycol in. And the conditions for this one was, as we look again, is 97 degrees and 3 bars. So that's what we're gonna input now. 97 degrees and 3 bar, and in mole frag is 1 for ethylene glycol. And the mole flow, in principle, that's what we want to know. The mass flow that is required to have a temperature of 42 degrees at the outlet of this stream. But we have to start with a normal value and see if the heat-ex block can converge. And once this is done, we can just input a normal design spec to get the exact flow that we need for the system. But in this one, let's try with perhaps 3,000 kilograms per hour and see if we can get the block converged. So now we have the hot stream and the cold stream. And now we're gonna start with the heat-ex block. Let's call it heat-ex. And now you have to see that the order is really specific. The cold stream must be here and the hot stream must be here. So be careful with this because it can give you some errors, and it's just about ordering. So the cold stream, which is the freon, must be here, and the hot stream, well, the hot stream will be here. Let's put it in a better shape. And now the outlet is here. So this should be R12 out, and this should be ethylene glycol out. So now we have the strings connected. Now we need to solve the block. And for that, we know that we need a shortcut estimation. So the model fidelity must be shortcut. The calculation mode is designed, but you know that you can also have different modes. But for this time, let's keep it simple and let's go with the design. And the specification will be, in this case, the heat duty that we calculated previously in task 1. And you can find it here, exchanger heat duty. So the value in kilowatts that we found was exactly 180,145 kilowatts. And here you can have the minimum temperature approach, in which you know that, okay, the minimum we need to reach is 15 degrees. So if we don't have this condition converged, then Aspen will give us an error. So now let's start with 15 degrees. The required input is complete. So now we can start with the simulation and see if we did something that could converge the heat-ex block. No warnings, no errors were issued, which is a really good sign. So now let's see the results in here. You can see now that because of the duty, the 27 degrees as a target temperature was reached because we calculated that before, regardless the heating fluid. But now we have to see that we need to reach a temperature of 42 degrees at the outlet of the ethylene glycol, and now we're getting 7, which means that we need to reduce, well, we need to increase this amount of heating fluid because we need to increase the temperature at the outlet. So the more we input, the higher the temperature is going to be at the end. So for now, we can do a normal design spec, and let's try it now. The design spec that we're going to create is going to be relatively simple. So the variable that we want is the temperature out of the stream variable. It's a stream variable, and it's going to be ethylene glycol out. It's going to be temperature, and it's degrees Celsius. And the expect is that T out must be 42 degrees and tolerance of 0.01, for instance. Now the variable must be ethylene glycol in mass flow. So we can start with mass flow, ethylene glycol in, ethylene glycol, and let's start from 0 till 10,000 kilograms per hour. So now let's run it again. You can see the iterations. No warnings, no errors were issued in this input translation. So now we can see the results of our design spec, and we can find 42 degrees, well, 41.99 with 4,781.28 kilograms per hour. So in this way, we already know how much ethylene glycol in kilograms per hour we need to input to this shell and tube heat exchanger to get a target temperature of 27 degrees. And with this one, task 2 is fulfilled. But just so you know, we need to make sure that the minimum approach was indeed well calculated. We did that, we knew that before, but if we have the TQ curves, which was also a requirement in this exercise, you can see that the minimum approach will be just the temperature difference at both ends. And in this one are way higher than 15 degrees, and that's why Aspen converged the heat-x. If not, it would have given us an error, and we have to be more specific in our data input to get the heat-x converge. So this should be the temperature profile in both streams. And with this, we conclude with task 2. And now we're going to be talking about task 3 at the end of this video. So thank you for joining in task 2. Now I will see you in task 3. Bye bye.